Ladies and gentlemen, would you please welcome Jeff Sharkey.
Well, hi, everyone. My name is Jeff, and I'm a software engineer on the Android team. And today, we're going to talk about doing more with less. And along the way, we're going to build an app that's worth $1 billion. So where do we get started? First, I think we all can agree that we want to build a great user experience, an experience that's fast when we're interacting with our app in the foreground, but also an experience that's lightweight when we're running in the background. And really, this all comes down to resources. Resources like CPU, and memory, and disk I/O. And on a mobile device, these resources are constrained, and they're shared amongst all the apps running on the device. So if we want to build that great user experience we just described, we're going to need to work together. So today, as we build an app, I'll show you how we can work together and how we can do more with less. So let's start by building a simple photo gallery app made of two activities. The activity on the left is just a simple overview of the photos the user has taken on the device. And there's a second activity on the right that we can drill down and see a detailed zoomed-in view of a specific photo. So to build this today, we'll be using the Media Store content provider on the Android platform. And we can query the images.media.external content URI. And when we query that, we'll get back a cursor, which is a list of all the photos the user has taken on the device. One of the columns that we're going to ask for in that cursor is the _ID column. And that'll give us a unique ID for each photo the user has taken on the device. With one of those IDs, we can use the thumbnails.getThumbnail API to load a small scaled-down version of one of the photos the user has taken. With that _ID, we can also build a URI and use OpenInputStream to open a full-resolution version of that photo to show to the user. And just a note today, I'll be digging through some code snippets a lot in the slides, but I'll give you guys a link at the end if you're curious for the full app. All right, so in the background, I'm going to be using the loader pattern to actually perform that query and get that cursor. When that cursor comes back, I'm going to hook it up into a simple cursor adapter. So each of the views that I'll be showing in the grid view, in the grid layout, or the grid view, is just going to be an image view for each of the items, for each of the photos in the list. And when I go to bind the view, I'm actually going to kick off an async task to go load that thumbnail on a background thread. Because loading thumbnails, we're going to go to disk, and disk I/O can potentially block. And we don't want to block the main thread of our application. So hopefully everyone is familiar with async tasks and how to use them, that pattern on the platform. So here's the actual thumbnail async task, what I'm doing. The argument coming in is that photo ID, and the bitmap is that small thumbnail. And here in the middle in that background thread, I'm using thumbnails.getThumbnail, load the bitmap, pass it back to the main thread, and assign it into that image view to show to the user. So let's go ahead and take a look at this on the device today. Switch to the device. Is it there? There we go. So here's some photos I've been taking around the conference. I can scroll back and forth. And notice the scrolling is nice and smooth. It stays smooth because we're doing that disk I/O on a background thread. But at the same time, if I scroll back and forth, you'll notice that we still end up loading the photos multiple times. Photos that we loaded just moments earlier, we're now actually having to go to disk again. We're kicking off another of those thumbnail async tasks and doing a bunch of duplicated work. So we'd like to avoid that if possible. And one way to avoid that is caching. And there's a couple different ways of writing caches on Android. One way would be to use soft references. But soft references don't give us much control over when and how that memory is cleared by the VM. So instead, we're going to use an LRU cache. So let's go back to the slides. So an LRU cache, LRU in this case, just stands for least recently used. So just a quick overview. An LRU cache is a bounded data structure. It has a bounded size. And it keeps track of how recently items in the cache, how recently we've accessed them. And thinking of our thumbnail example today, photos that the user may have just recently looked at are kept fresh in the cache near the front. But thumbnails that maybe are off in the periphery that the user hasn't looked at in a while are closer towards the end of the cache. So as the cache needs to make more room, it can evict the oldest items in the cache. So Android actually offers an LRU cache implementation. And it's been in the platform since API level 12. And it's also in the support-v4 library. So you can use it on a wide range of devices. So let's use it here today to build our thumbnail cache. So LRU cache is a genericized class that takes two types, a key and a value. So today, for our purposes, we'll map from a long to a bitmap, where that long is that photo ID is the key of our cache, and the bitmap is if we've loaded one of those thumbnails in the past. One thing that's nice about LRU cache is that it offers us a size of method that we can override. And this gives us an opportunity to communicate the size of a specific item that we're storing in the cache, how much we'd like it to count against the maximum size or the bounded size of our cache. In this case, I'm just going to return the number of bytes that the bitmap object actually represents in memory. And just as an example, a typical 320 by 240 bitmap uncompressed in memory is about 307K, just a ballpark example. And you'd expect the two last methods here, just a put and a get, that you'd expect from a typical caching API. We can put items in, and we can attempt to see if an item is in the cache with the get. And it'll return null if it's a cache miss, if the item isn't in the cache. So let's go ahead and hook this up into our application, the one we've been writing today. But the first question that we need to answer is, how large do we make this cache? It's a bounded size. If we make our cache too small, it's not going to be very effective. We're still going to end up going to disk quite frequently to load data if it's not in the cache. But if we make our cache too large, we actually risk exposing our application to an out-of-memory error. Because whatever we're allocating inside of LRU cache, we need to keep enough memory for the other parts of our application, like our activities and layouts that we're inflating. So a good place to start for a cache size is the getMemory class on Activity Manager. And this returns a size in megabytes of how hard of a memory limit we should impose in our application to let the system work its best. So some typical examples for this are about 48 megabytes on a Nexus S device and 64 megabytes on a Galaxy Nexus. And the reason there is Galaxy Nexus has a gigabyte of RAM, so it has more space that applications can take advantage of. OK, so in this case, I'm getting the memory class, turning it into bytes, converting from megabytes to bytes, and then I'm creating that thumbnail cache. I'm starting, a good place to start for the cache size is dividing that class, that memory class by 8. So keep in mind that we have to keep enough headroom for the rest of our application, those activities and layouts. So dividing by 8 is a good starting point, but we'll definitely want to look at our application and tweak that value over time. Again, keeping in mind those two trade-offs if we make it too small or too large. OK, so now we have our cache. Let's go ahead and hook it up in those two classes we were looking at earlier. First, in the async task, once we've loaded the bitmap from the thumbnail API, we're going to store it in the cache, just in case we may be able to take advantage of it in the future. Then over in the cursor adapter, when we're binding one of the views, we'll check the cache first, just to see if we get a cache hit, if that image has already been loaded and it's still around for us to use. If it is, great. We can set it immediately and return instantly. But if it's not in the cache, if it's a cache miss, we're still going to need to kick off that async task to go bootstrap to load the thumbnail the first time. So let's go ahead and take a peek at this on the device. So switch to the device. We have the device. There we go. And in this case today, it's the same app, and I just have a menu item where I can enable the cache. The first thing that you'll notice is down in the bottom right, I'm actually surfacing some statistics about the cache, how effective it is. And these statistics are automatically tracked by LRU cache, the class in the platform. And I'm surfacing them here just to see how effective our cache is. But they're available if you're interested for your own apps. So now as we scroll, through our list, you can see that we still have to bootstrap. We still have to go load the items. But now, as we scroll back and forth over region, those photos are coming in instantly. And I can scroll all the way down and back up and through the list. And now, like the items, a lot of them are in the cache, and they're filling in perfectly. So I have a nice, smooth UI. And at the same time, I'm avoiding all of that duplicated disk I/O. I'm taking advantage of the memory on the device to make my app faster. And we can see how much of a difference that's actually making in those statistics. The number of cache hits we've had down in the bottom right there is 449. So just in this quick example of flinging back and forth in the list, we've avoided having to go to disk and load data over 400 times. So caching is a great example of how we can do more with less on the device. But now you might ask the question, how much memory are we actually using? And there's a great utility that can help us answer this question. So let's go back to the slides. Back to the slides. So today, there's a great utility called procrank. So let's actually use that on the device today. Shell procrank. And procrank is a list of all of the processes that are running on the device, sorted by how much memory they're using. Now in Linux, there's many different ways of slicing and dicing memory usage, and that's what these various columns are. But the number that we're most interested today is USS, or the unique set size of our application. And I'll come back to that in a moment. But first, Android at a high level is a multitasking operating system, and we want to enable users to quickly switch between multiple applications. And the way that Android does this is it caches applications in the background. When you switch between an application, between apps, it keeps your process running, including any memory that you've allocated. But at the same time, if a user is in a foreground app, and that foreground app needs memory, and the system has used up all of the physical memory on the device, the system needs to come up with that memory somewhere. So it begins looking through this list of cached background applications, looking for apps that it can kill to reclaim that memory to be used by the foreground process. And that's where that USS metric comes into play. USS is a rough metric of the memory the system would reclaim if it killed that process. So if we look at this list, our application, this gallery app that we've just written today, now that it's caching all of that data, it's at the top of that list. If some other process on the system comes to the foreground and needs memory, our app is actually first in line to be killed on the device. And this will end up giving us a bad user experience. If our app is killed and the user does want to come back, we have to start from scratch. We have to fork the zygote. We have to inflate our activities and any layouts that we were showing to the user. So if possible, we'd like to stay cached. And there's a way to do this. Android offers, it doesn't have to stay this way. We don't have to keep using all this memory. Android offers a set of callbacks where we can help release some of this memory back to the system. So the first callback is on low memory, which has been around since 1.0 in the platform. But the downside of that is that method, that callback, is only called after all of the background apps have already been killed on the device. So if we're running in the background, it's probably not very useful to us. But we would never receive this callback. We would be killed. So starting in Ice Cream Sandwich in API 14, there's a new API. There's a new callback called onTrimMemory, which gives us a much more granular view of the system state, of how much memory the system would like us to release back. And that level that it provides as the argument is a value between 0 and 100, indicating how aggressively we should try to return memory back to the system. And we'll dig into that a little bit more in a second. So both of these methods, both onLow memory and onTrimMemory, are ready to override today on activity, fragment, service, content provider, and application. But if you find yourselves outside of one of those life cycles, you can also implement the interface and call register component callbacks to use that if you're outside of one of those life cycles. So let's actually hook this up in our app that we've been writing today. So here, so we talked about how there's a trim level that comes in that's between 0 and 100. There's actually a handful of values that are well-defined. Trim memory complete, moderate, background, and UI hidden. And those have been defined in Ice Cream Sandwich and API 14. Those are well-defined. And we can check against those levels, check against those constants. But we don't want to do a direct equality check because new levels could be introduced in the future. So here in this code sample, we're going to start by checking against the most aggressive setting, or the aggressive trim level that we're interested in. So in this code example, we're checking if the level is greater than trim memory moderate, which actually has a value of 60 under the hood. And this trim memory moderate indicates that our application is nearing the middle of the list of cached background applications. So the user hasn't interacted with our app in quite a while. They're off doing maybe some other tasks on their device. The user may come back to our app, but probably not. So we can use this as a good hint to release the memory that we've been using for our thumbnail cache. And that's what we're doing here. We're going to the cache and calling evict all, which will return all of that memory. Next, we'll be checking for a slightly lower level, trim memory background, which has a value of 40. And this is a hint from the system that our application is just entering the list of cached background apps. So the user was using us just recently, and they may have switched away to some other tasks. And we're going to use this, and this is a place where the fact that we're using an LRU cache becomes valuable. So remember earlier that LRU cache keeps track of which items we've used recently, and also which ones are the oldest items in the cache. So we can use the trim to size method to actually evict or release the memory for the oldest half of the items in our cache. So if the user does decide to come back to our application, we still have some of the photos around the area the user was just looking, so it's fast and responsive there. But photos that are further off in the periphery, we've been able to release that memory back to the system. And just a side note, trim to size is actually a private method on the LRU cache class, but you can make a copy of the class and make it public if you need to use it. OK, another thing to note is that these callbacks are purely advisory. there's no guarantee that the system will call them. In fact, if the system is under extreme memory pressure, it may end up killing our application before it has a chance to even deliver the callbacks. But if we release memory through these callbacks, the system may be able to keep our app cached longer, which is a better user experience. We're able to launch our app faster if the user does come back. All right, so now our app, we have our gallery app. It's running fast. We're caching items. We're releasing some of that memory back to the system as we're running in the background. So let's go ahead and add another feature. Let's add the ability to star photos, keep track of photos that are interesting to the user. And we can do this using an action mode, which is something introduced in Honeycomb. We can do this by using the set choice mode multiple modal. And when we do that, when the user long presses on one of the photos in our list, our action bar will actually swap, and it'll be replaced with an action mode, where the user can select various items, various photos from the list, and then apply an action to them, like starring or unstarring. And the one thing that I want to look at today is conceptually how that set of items is represented, the photos the user selected. So conceptually, it's a map from an int to a Boolean, where int is the position of a photo in the list, and a Boolean is indicating if the user has selected that item or not. And we could store this as a hash map from an integer to a Boolean. But instead, grid view and list view on the platform return these values as a sparse Boolean array, which is an Android-specific data structure. And the reason for this is autoboxing. Autoboxing is a language feature which transparently converts from primitives, like int, into instances of objects, like java.lang.integer. And autoboxing is powerful because it allows us to mix primitives with genericized data structures, like hashmap, but it comes at a cost. Each of those boxed primitives, the java.lang.integer that we're forced to allocate, adds load to the garbage collector on the system. It's an actual object allocation. And sometimes autoboxing can sneak in if we're not careful, if we're not aware of it. So here's two code snippets. The one at the top, we're actually looping just from 0 to 100 and adding up the total of the numbers inside. And this actually allocates 0 objects because it's working with primitives the entire time. But just that one simple change from int to integer, that same loop that produces the same resulting output value ends up allocating over 96 objects. And the reason for that is that at each point in the loop, we end up having to unbox that total value, add it to the primitive, the current I, and then rebox it back into total. So this is where using autoboxing like this can add overhead to your app. And this is where sparse Boolean array comes into play. Sparse Boolean array allows us to map between primitives while still avoiding a lot of that overhead that comes with autoboxing. So here's an example looking at storing 100 key value pairs in various data structures. And the first one at the top is the one that we were just looking at, mapping from an integer to a Boolean. Now, if we store that in a hash map, we end up allocating over 200 objects under the hood. This is because hashmap internally allocates a hashmap entry for each pair that we're storing. But if we were to store that same data, the same 100 key value pairs, in a sparse Boolean array, it takes many fewer objects. In fact, the majority of the data is stored in just an int array and a Boolean array, which from the perspective of the garbage collector are just a single object. And there are many other there are many other data structures. If you find yourself using one of these data structures on the left that's mixing generics and primitives, try looking at using one of the Android utilities instead. It offers the same functionality, but it's much lighter weight if you're looking to store that data. OK, so now we have our set of stored photos that the user is interested in. Let's go persist it, and let's use SQLite. So SQLite is powerful because changes that we make are ACID. They're atomic, consistent, isolated, and durable. So let's write some code to do this. We'll loop over the set of items the user selected, so the selected photo IDs. And for each of them, we're putting that ID and the starred value into a content values. And then we're going to be calling SQLite database.insert and inserting it into a starred table under the hood. And this code works. It actually successfully stores the data. But db.insert, in this example, makes those guarantees, those ACID guarantees, each time we call insert. And this overhead, the overhead of making those guarantees, can add up very quickly. So instead, we can manage that overhead ourselves by wrapping those mutations, those changes, inside of a transaction. So it's the same core code here, the same for loop. But before we call into that, we're calling a begin transaction. We're opening a single atomic transaction, performing those mutations, and then we're setting our transaction successful and then ending it. And this ends up having a big impact. So here's an example along the x-axis of storing a number of those values. So from 20, 30, up to 100 different values increasing along the x-axis. And along the y-axis, we're looking at the actual number of bytes that we ended up writing out to disk under the hood to actually persist that data. So with the original code that we were looking at, we can quickly see that that overhead, it climbs up into the right. Because of that overhead, with each of the DB inserts, we're making those ACID guarantees. But by wrapping it inside of a transaction, we're actually reducing a lot of that overhead because we're performing it as a single atomic transaction. So then you might ask the question, well, why not wrap all of my mutations inside of one big giant transaction? And this probably isn't a great idea either. And the reason is in SQLite, by default, transactions are exclusive. And this means while someone is holding a transaction on the database, no one else can read or write to that database. And this is particularly visible if you have something like a sync adapter in a background thread that's syncing data down from the web, and you also have UI that you're showing to the user, where you're showing data to the user. The UI may want to query and update that data to show to the user, but it may end up getting stuck, waiting for a transaction from the sync adapter to finish. So we can solve this. We can solve this by inserting yield points into our transaction. And so here's an example of this. We're doing our db.insert that we've been doing through the last couple examples, but now we're inserting this method, yield if contended safely. And what this does is when we call into it, if the database is contended, if someone else is interested in performing a read or a write on the database, when we call in here, it will end our current transaction that we're executing, letting that other query, that other read or write, proceed. And then, when that's finished, it'll begin another transaction before returning control back into our loop. And the nice thing is, if the database isn't contended, it'll just return quickly. So we'll still be able to perform a lot of our data changes inside of a single transaction if there's no one else waiting on the database. But if there is, now we have an opportunity. We're still using a transaction to apply the changes quickly, but our UI can now be much more responsive. Instead of potentially showing a loading spinner for several seconds, those queries can still come in and read out some of the data to show to the user. Cool. So now I have my gallery app. It's fast. I'm starring photos to show to the user. I don't know, but I've been taking these photos around the conference, and they're just a little boring. I guess if I had a way to make them more interesting, maybe if I had an SLR camera with some color filters, I could spice things up a little bit. But carrying around equipment like this, it could potentially get a little unwieldy, a little heavy to carry. So I guess we could write some code to do it. There's a couple different ways. So if we're going to be writing some image processing code on Android, we'd want to make sure that it's fast and efficient so that we're not wasting resources. So there's a couple different ways of writing fast code like this on Android. One option would be to use the NDK, but there's another way to write C code called Renderscript, and that's what we're going to use today. So first, before I jump in, I'll talk at a high level about 3 benefits that Renderscript offers us, or 3 ways that it lets us do more with less. So first, Renderscript automatically scales to whatever hardware we're running on top of. And Renderscript does this by taking our input, which could be a bitmap, and splitting it into small pieces, like pixels, and then running code on each of those pieces. So in this example, if I have a photo up here in the left, it's going to split it up into those pixels, and it'll run an algorithm on each of those pixels. And because it splits the work into pieces, Renderscript can parallelize this work by creating a separate worker thread for each CPU core in the device. Another benefit of Renderscript is that it targets all architectures, including ARM, x86, MIPS, and beyond. And Renderscript does this by splitting compilation into 2 stages. First, it compiles our Renderscript code, our effect.rs file in this example, into an intermediate bitcode, which isn't specific to any architecture. Then it packages that bitcode inside of our APK. Then when our app is installed on the device, a second backend compiler takes that intermediate bitcode and compiles it into optimized native code for whatever architecture and optimizations that device may have. And finally, Renderscript generates JNI glue code for us. If you've written code with the NDK in the past, you've probably had to maintain JNI glue code to jump between Dalvik down into your native code. But Renderscript generates a Java class and methods to represent your script, making it easier to jump between those two worlds. So let's dig into an example today. Let's say we want to build a simple Duotone style color effect. So here's an example starting in the top left with a single pixel. Maybe that's like a red, a lighter red. And the first thing we're going to do is take the intensity or the brightness of that color. And that gives us this, it's a lighter gray. We're going to use that to map onto a gradient, a color gradient between two values. So between two values. In this case, if the brightness of the intensity of the color is darker, we'll pick more towards more of the greenish or bluish value. But if the color is brighter, we'll pick more towards the yellow along this gradient. And in this case, this color ended up giving this, this greenish value. And then we're going to combine together, we're going to mix together those two values. So we mix the original red with our green, and this gives us more of this olive color as an output. So let's go ahead and write this code to make it work. So here's some Renderscript code. The first thing at the top is we're defining a handful of pragmas to talk with Renderscript to define what we're looking to do. And the next thing, we're defining a constant that we'll look at in a moment. But the thing I want to focus on first is this root method, where we're defining it. And the root method takes two arguments, an input pixel and an output pixel. And the data types of these arguments is, in this case, is a uchar4, which is a vector type of 4 unsigned characters. So it's, in our case, an unsigned character is similar to a byte. So you can think of this as 4 bytes in a single type. And bytes, so in this case, the 4 bytes here are the 4 color channels, alpha, red, green, and blue. So it's essentially a pixel at a time. The first thing we're going to do is convert that incoming pixel into a float 4. And this is another vector type representing 4 floating point numbers. The next thing we're going to do, so we have this input color, we're going to take the dot product of that with another static float 4 that we have outside of our method. It's a global. And we take the dot product between those two values. It's going to give us the intensity or the brightness of that pixel. And I'll divide to give us a range between 0 and 1. So next, I'm going to add a couple global variables, dark color, light color, and strength. So those dark color and light color, those are another set of float 4s, which represent the two ends of that gradient that we were looking at. And finally, strength, which is going to indicate how strong we want the effect to be. So if we have a strength, and we'll see how to use that in a moment. The next thing down in our root method that we're going to add, we're going to use a method called mix. So Renderscript offers us a library of methods that are useful for performing mathematics. So there's mix. There's also normal trigonometric functions that you might be used to, like sine and cosine. But we'll use mix today because that offers us the ability to map between that dark color and light color. So we'll use mix between the dark and light, using intensity as the key, so that if our value is 0, it's going to pick dark color, and so on along that spectrum. And this is going to give us a tone color, so another float 4 color output. We're going to multiply that by intensity, which returns some of the original brightness to the current pixel we're working on. And finally, we're going to use mix again to blend between that original input color, the red, and a final toned color along a gradient. And we'll use strength as our value. So if our strength is 0, we're just going to use the original input untouched. And if it's 1, we'll use completely the toned color. And we're going to convert that back into uchar4, and that's our return value from this method. So this is all in C. So let's jump over to Java and hook this up. The first thing we're going to do is we're going to load the bitmap, load the photo that the user wants to process. And so in this case, I've built up a content URI that I can go and load. And I have a load bitmap method that is going and opening that content URI, reading out the data, and inflating it into a bitmap. So I have my input bitmap. Then I'm going to create an output bitmap, which has the same width and height. So it's identical dimensions and configuration to the original input. So one thing to note is that bitmaps are Dalvik managed objects. So they work great when we're doing other things in Dalvik, like showing images to the user in an image view. But when we work with Renderscript, we need to convert our data, we need to copy it into Renderscript managed objects, which are allocations. And that's what we're doing here on the second chunk. We're using a helper method called createFromBitmap to convert that input bitmap. Under the hood, it's creating a 2-dimensional allocation of uchar4s to represent our bitmap. And then it's copying that data from the input bitmap into the allocation. And finally, I'm using allocation create typed to make a mirrored output allocation, which we're going to use for the output of our effect when we're done and we want to show it to the user. OK, so let's actually hook up the effect. So remember a couple slides ago, I talked about how Renderscript generates JNI glue code for us. So when we defined our effect.rs file in the SDK, and we compiled, it generated a Java class called script_c_effect, which we can instantiate and use over here in Dalvik. So that's what I'm doing at the top. I instantiate that script, and it also automatically created a handful of those methods, the set dark color, light color, and strength, and I'm able to call those nice and fast. And finally, I'm calling script.forEachRoot. And this is what's going to take our input allocation, our two-dimensional bitmap, split it up into those small pieces, and run our root method on each of those small pieces, on each of those pixels. Finally, I'm going to copy the output allocation back from Renderscript into Java, or into Dalvik, and then show that bitmap in an image view. So let's take a peek at this on the device. Switch to the device. So here's the gallery app that we were using. Let's go ahead and pick a photo. So let's say one from like the after hours last night. So I can go apply the Duotone effect. So here's that strength, and as I drag back and forth, it's updating that global variable and pushing it down into Renderscript, and then kicking off a for each. So each time I'm changing the value. So if I pull the strength all the way up to the top, now I'm picking along the side of, just applying the Duotone color effect. I'm not using any of the original colors. And then when I pull it all the way down, using all the original pixels. So if I crank it up, I can change like the dark hue down to like red, or maybe I want it something green, and the light hue maybe like red. Maybe find a sweet spot right in the middle. Cool. Now my photos are looking a whole lot better. And I'm actually doing a great job with Renderscript of being able to apply them in a couple different ways. So let's jump back to the slides. So remember earlier, I mentioned there were some benefits that Renderscript offered us. But really, we've only scratched the surface. Today, in our root method, we only looked at a single pixel at a time. But in reality, we had access to the full allocation in each of those, each time we were running through the root method. So this could enable us to write effects, maybe like a blur effect, where we needed to look at neighboring pixels, or like an image filter, or like an image detection or a feature detection algorithm. Another thing to note is that allocations are much richer than just these two. Today we just looked at using a 2D allocation of these UChar4s, which represent bitmaps. But there are many other types of allocations we can create. For example, a one-dimensional allocation of floats, which could represent float audio data. So jumping back to those original things that I mentioned, so Renderscript allows us to scale automatically to the hardware we're running on top of. So here's an example of how long it takes to process a 5-megapixel image, so identical image on various hardware. So on a Nexus S, it takes about 1,200 milliseconds. On a Galaxy Nexus, which is a dual-core device, to process that same image, it only takes 400 milliseconds. And the reason for this is under the hood, Renderscript is creating those two worker threads, one for each of the cores on the device, and it's splitting up that work equally for us. So this is with the same code. We didn't make any code changes, and it's scaling it to the hardware we're running on top of. And also on the Nexus 7 that we announced yesterday, which is a quad-core device, it runs even faster, 240 milliseconds. And again, because it's creating 4 of those worker threads in the background. And there were no code changes on our part. So today, on most of Android devices, we're just scaling on the CPU. But Renderscript is designed in such a way that we can scale and run computations like this on the GPU in the future. Another thing, like I mentioned earlier, is that Renderscript targets all architectures, including SIMD-style optimizations. So if you're familiar with Neon on ARM, or the SSE family of instructions on x86, Renderscript automatically emits these optimized instructions when they're available. If we had written this code with the NDK, we would have had to write separate versions of our algorithm with separate compiler intrinsics for each of those instruction sets. But because we wrote it with Renderscript, we wrote our algorithm once, and that back-end compiler took care of emitting those optimized instructions for us. And finally, Renderscript isn't designed to replace the NDK on the device. It doesn't offer access to Bionic libc, for example. But Renderscript is really designed to be best at compute-intensive work. And that's what we used it for today in our example. So Renderscript is a great example of doing more with less. We've been able to scale automatically to the hardware we're running on top of and use optimized instructions with much less coding work on our part. OK, so we have this visual effect. Let's say we want to apply it automatically. And we can do this on Android. There's a new powerful broadcast intent that was introduced in API 14 that's kicked off that the system sends whenever a new photo is taken. It's the new picture intent. So here in our Android manifest, we can listen for it using a photo receiver. And that's the top definition here. And then down below is the Java code corresponding to that, where we define our broadcast receiver. And when we receive the broadcast, we'll check a user setting, if the user has enabled or disabled this effect. If they want it applied, if we want this, the duotone effect that we just applied automatically, then we're going to go ahead and kick off that work in an intent service. And the reason is, if we did it right here in this broadcast receiver, we'd potentially expose our app to an ANR. And because we're going to do that disk I/O and the compute-intensive work, we want to kick that off into an intent service. So this code works. This gets the job done. It works. But the downside is if the user has never enabled this feature in our app, the system is still going to wake us up. It'll still deliver this broadcast, and we'll run our code. We'll come in. We'll check that flag. And if it's disabled, we're just going to return. So we're actually wasting system resources. The system is waking us up, and we're not doing anything. We're just returning. But it doesn't have to stay this way. So there's a great way that we can use, there's a great API we can use on Package Manager called Set Component Enabled Setting. And we can use that today to turn on and off our broadcast receiver dynamically. So the one change we're going to make at the top in our manifest is we're going to make our broadcast receiver disabled by default. So we can use that with the enabled equal to false flag here. Then later, at runtime, when the user is interacting with our app, we can programmatically enable and disable that broadcast receiver. So when the user turns on that feature and wants the effect applied automatically, we can turn it on, and we begin receiving these broadcasts in the background from the system. And then if the user does decide to turn it off, we can just as easily turn that broadcast receiver back off to avoid the extra overhead. So today we just used it for the new picture broadcast, but there are many other broadcasts that are maybe more interesting. And it's especially important for common broadcasts across the system, like connectivity change or packaged added. So say, for example, today in our app, if we had written a photo upload queue, we were uploading photos to the cloud that the user had selected. If that queue is empty and we listen for the connectivity change event, our app would be woken up, and we wouldn't have anything to do. Our queue would be empty. So that would be a great opportunity for us to use this API to turn off our broadcast receiver when we don't have any work to do, when there's no work pending. Cool. So today we talked about, just a summary of what we talked about. We built a gallery app. We made it fast by using caching. Then we listened to trim callbacks to reduce our memory usage and return it back to the system to keep the system running nice and smooth. Then we looked at the overhead of autoboxing and how we can avoid it using utilities like sparse Boolean array. Then we looked at SQLite and transactions and how they can help us save disk I/O as we're saving to disk, persisting data. Then we looked at using Renderscript as a great way of writing visual effects that scale automatically to the hardware we're running on top of with less coding work on our part. And then finally, we looked at broadcast receivers and using them efficiently to enable powerful effects without overhead on the system. So today, we built that user experience that we really set out to build. Our app is fast in the foreground, but our app is also lightweight when it's in the background. And because we work together with the system, we built a great experience, not just for our app, but for the entire system. So hopefully today I've convinced you that on Android, you truly can do more with less. Thank you. So I think there's two mics. If anyone has questions, there's two mics, one in the front and the back of the room. Feel free to jump up and ask questions. If you're interested in the app that we built today, the source code is available. There's a link up there if you're interested. It's open sourced under Apache 2.0. Yeah, go ahead in the front.
Okay. Hi. Can you compare OpenGL shaders with Renderscript in terms of performance?
Sure. So in this case, shaders. So there's two parts to Renderscript. There's a OpenGL graphics part, and then there's also a compute part. And I don't know GL shaders, which part of Renderscript they would fit under. Do you know offhand?
Well, definitely for image processing. So what you have done can be done with GL shaders. Instagram is doing it, or Pat. We also do gel shaders
Okay.
because they're enabled in 2.3. But if Renderscript can perform better, so is there value in like trying to support Renderscript in Honeycomb Plus, or just go with gel shaders?
That's a great question. I don't know the answer off the top of my head. If you come up and catch me afterwards, there's somebody around that we can find to answer your question.
All right, thank you.
Thanks. Take one from the back if anyone's there, or from the front, either way.
Hey.
What's up?
Just wanna ask about the autoboxing feature, that Java has. I read on Stack Overflow that internally, for example, in the Oracle JVM, they handled some sort of pool to prevent this creation of objects. I was wondering, does this feature is inside Dalvik, or?
So I can't speak to the details of other VMs. The one thing I know about, so for example, integer in Dalvik, the implementation that's there, it does actually create a handful, a small pool of integers for like small values, like from -127 to like +127. So it can share some of those values, but not the entire range.
All right. So my second question would be like, you managed to use a sparse array for certain things in order to prevent the creation of several objects. But once you are gonna use it like a key in a hash map, you don't use it. Like, what's going on there? Like, I mean, you put that long as a key, but you are creating several objects there, or also hash map helped you in that way?
So you're talking if I use different types of primitives?
No, when you use, for example, a long as a key in a hash map.
Or in the LRU cache?
Yeah.
Right, so LRU cache, I still have that overhead of autoboxing in that example. We could write a version of LRU cache where we changed the key to just be whatever primitive we needed, but we would have to write a different class for that. It's, again, generics are powerful, but it's something to be aware of. So if we needed our LRU cache to be really fast, we may write a specialized version that avoids autoboxing.
Thank you.
Yeah. Next.
I have a question on the LRU cache. You said it started with API 12, and it's backward compatible with the support for library.
Yeah.
What's the overhead of using the support library?
It's small, so it's the support library is going to pull in Java like class files that into your application. It's a jar library that you attach on. If you use something like ProGuard, it can strip out all of the other parts of the support v4 library that you're not using.
Okay.
So that can help reduce the overhead. It'll just pull in the pieces that you're using.
Okay, so we have an APK right now. So you think it'd be worthwhile just for the sake of the LRU cache, since we're supporting versions 11 and up, just for the sake of the LRU cache, we don't use the support v4 library right now, to go ahead and use the support v4.
I would say go ahead and pull it in if you also apply the ProGuard, because it'll help strip out the resources. The worst case, the source code is available. It's licensed under Apache 2.0, so you could copy the class into your app, just that single class.
And what's the backward compatibility route for Renderscript?
Sure. So Renderscript, I forgot to mention that, it was originally introduced with Honeycomb. And that's the API, that level that it was originally introduced with.
And it has backward compatibility layer also with it?
So it's API level 11 and up, which is increasing. There's more devices, like the devices we handed out today, have the higher API levels.
Okay. All right. Thank you.
Yeah. Next.
I have just two quick questions. Actually, to follow up on that, you said it's available in the later version of the API, but is it available from the support library?
No, Renderscript isn't.
Okay.
Because, and part of it is that backend compiler that we saw, that needs to live on, it needs to be tailored for whatever device it's running on. Okay. So it really needs to be targeted to the device.
Okay, and the second quick question is Renderscript capable of doing more complex image processing algorithms where you need to actually look at neighboring pixels to compute your current pixel?
Yes, yes. So when you were in that root script, today we just looked at a single pixel at a time. We had full access to get whether neighboring pixels or across the entire allocation. So we had access to all that data if we needed it.
Okay, thank you.
Yeah. Next.
Hi. Is there a difference in performance or optimizations between async task and async task loaders? Can we use the loaders instead of the async tasks?
So the one thing that loaders offer you is that if a result has been loaded and the configuration changes, so like you rotate the device, the loader will take care of sending that across to the new activity. If you did it with an async task, you'd have to manage and bring that along with you. So an async task loader, it brings the power of both worlds. You get the benefits of loaders and the async task.
Okay, and so there isn't any performance issues with the the loaders?
No, in fact, cursor loader, if I remember correctly, actually extends async
Yeah.
task loader. So it's using it under the hood.
Okay, thank you.
Yeah. Next.
Thank you very much. I have a question about services. You talked mostly about foreground Android apps
Yeah.
and best practices. Is there a talk, or have you given a talk about how to use make sure your service is not abusing, being a good citizen, and can use proc rank for that?
So proc rank is just going to surface the memory usage of your process, of your application. And it doesn't offer any details into which parts of your application are using that memory. So one good strategy, you're talking about services. Intent service is one of my favorite utilities because it helps manage and stop as soon as you finish processing the intent you've sent it. It takes care of shutting down the service. So that's probably one of the best practices for services.
No, but I mean, when you write your own service, let's say I'm listening to the GPS.
Yeah.
I have to write a service or a C2DM service, and I'm abusing the system. How do I know?
So that's a great question. So one way that you could potentially see that is by looking at, so in the settings UI, and you go into apps, there's a list of running applications on the device. So you can see if your service has been running for a long time on the device. So that can be a signal, like if you don't expect your service to be running. In addition, so these are ways of tracking down. You can also look at like the battery stats on the device to see if it's been using a lot of resources. Are you asking more like strategies on how to?
Yeah, best practices for debugging services or writing services, or did you give a talk on that too, or do you plan to? Or?
I haven't. I don't know. It sounds like a great topic. I know there's probably a lot of interest. Let's go ahead. Let's actually catch up offline. Because again, a lot of it is going to be dependent on the specific application. Some apps, maybe it depends on what you're doing in the service. Next.
Okay, my question is related to service as well. I found a lot of apps, they use long-run services.
Mm-hmm.
Yeah, like they use a lot of memory, right? So right now there's, I use C2DM, and also right now the cloud service is launched, right? So
yeah.
Actually it can solve a lot of problems, right? I think the Android should forbid the long-run service. Otherwise, like iOS, you only got 10 minutes, 10 minutes to do things on the background, right?
I think it's one of those things where, like, if you actually truly have a service running long, like, we want to enable the innovation. Like, somebody could have an important use for a long-running service. So I don't think we want to artificially limit.
Special permission is like basically destroy low-end phones. Yeah, services destroy low-end.
So I mean, and that's where it comes back. We give the UI to the user. If they notice that a service they're not happy with running a long time, we give the user control.
Yeah. Okay, another question is related to memory. So right now, do we need to explicitly call recycle for bitmaps?
So that's a great question. So the behavior internally of bitmaps has changed slightly over API versions between Gingerbread.
Yeah.
The one thing to be careful of when you recycle is that you need to make sure that it's not actively being used in your UI anywhere, because if you recycle it and it's still being used. So recycle under the hood, if I remember right, the implementation released the native allocation, right? And so at some point we moved that allocation to occur on the Dalva keep. So I don't know what recycle does in the newest versions. It's a great question.
Okay,
So if you meet up afterwards, we can look at the source code and see what it does.
Okay, so for the screen rotation, right? Should we always allow system to handle the rotation, or just handle the rotation by ourselves? That will avoid recreate activities, right?
That's a great question. So you're talking about like the handles configurations or configuration changes in the manifest.
Yeah.
My advice would be let the system handle all of those for you. And the reason being, like, even if you tell it to that you want to handle orientation changes on your own, so it may make your app fast, but there's still the case where another configuration could change and your app is still going to be exposed and it may be slow in that case.
If you have a lot of async tasks, you have to manually handle those async tasks, right?
Yeah, and that's part of why the loader pattern was introduced, because that helps solve those issues. It'll keep running in asynchronously, and then if the result is delivered either before or after the configuration change, it won't redo that work for you.
What do they call it again?
The loader pattern.
Loader pattern. Okay.
Yeah. So if you on activity, you can do get loader manager, and there's several APIs on there. Yeah.
Does the LRU cache handle data structures that might change size while they're cached?
No. So the data structure, that's why we overrode the method today. The only mechanism it has for counting it against the maximum size is whatever we report. So it's up to us to return how large the size in the LRU cache is.
Thank you.
Yeah. Next.
So the Renderscript example looked a lot like a pixel shader, but I'm curious if it can be used to do geometry and rasterize triangles and stuff like that.
That's a great question. So you're talking about like taking an input of like something to draw and then outputting pixels, like rendering?
Right.
That's a great question. I don't know the answer offhand. Catch us afterwards. There's somebody here that probably has the answer. Yeah.
If you have a multi-pass algorithm and you're splitting up the work across several cores, how do you synchronize?
Yeah. So you're talking about like you may have multiple stages of an algorithm that you want to apply to an allocation. So the output of one allocation may be the input to another. So one way would be to merge those algorithms. So it's C. You can call out to methods. Like you could call like method A and then method B and actually pass the data that way. But are you saying like the stages are fully dependent, maybe just not at the pixel level?
Well, even to take your example, if you have a filter, so you now have one intermediate output. Now you want to apply something else, and you want to access neighboring pixels. So you cannot just split the task up completely and just combine at the final stage. You want to have intermediate, basically synchronization of something.
I think I see what you're saying. So in that case, you'd actually, you could do a single for each method where you invoke to say process this allocation. Internally, it could process the first allocation and it would take like the output of one and input to the other. As far as like helping pipeline those things, I don't know what Renderscript offers under the hood. I think in the worst case scenario, you could run the for each, do an rs.finish to make sure that that processing is done, and then take the output allocation and pipe it into an input of another for each. Worst case. Thanks. Go ahead.
You discussed in talking about the multi-core capability of Renderscript that in the future Google would support, or the API would support GPU.
Yeah.
What are the options right now if you want to break up either a computationally intensive task to be parallelized or 3D rendering or something, and utilize the GPUs?
So at the moment, right, so Renderscript, the implementations that are shipping today just use the CPU side of things. In the future, we're working on enabling it on GPUs, but there's nothing that splits up that work today in that way. I've seen it.
Is there any other mechanism?
Not that I know of. Let's sync up afterwards.
Okay, thank you.
Yeah. Yeah, go ahead.
What is, given that you break the code into bit code, what's the difference between the Renderscript engine and Dalvik? Why couldn't this have been Java, for example? If we have bit code, byte code, and it's being chewed on beforehand, why isn't this part of Dalvik? Why is it something? Why is it different?
So Renderscript was designed. It's designed mostly for the compute-intensive side of things. So it's specific in nature. It's designed to crunch a lot of number crunching. Yeah. Dalvik is very general purpose. Okay. So it's maybe a design goal that may be different.
Okay, cool. Thank you.
Yeah. All right. Looks like we don't have any other questions. All right. Thanks everyone for your time today.